Hi guys, Dr. Justin Souther here, going through semester test 2, and I'm looking now at question 12, which is for 7 marks. Now, this is a really good question in a test and exam to gain marks on. It's 7 marks out of 45. That was over 15% just for this question, and it really is very, very easy if you know your differentiation rules, if you know your product rule, your quotient rule, your chain rule, and you know which to use when, and you don't get them confused. Okay, so 12.1, you were asked to, in all cases, differentiate the following and simplify where possible. 12.1, we've got y is equal to e to the x times the cot of x. So we've got two functions, the first function e to the x, the second function cot x. So of course when we differentiate we're going to use the product rule. The product rule says you differentiate the first, so the derivative of e to the x is of course e to the x, stays exactly the same, and then we multiply it by the second function untouched. So don't differentiate it yet. Then you add the first function untouched, so that's e to the x, and you multiply by the derivative of the second function. And in this case, the derivative of the second function, which is cot x, is going to be minus cosec squared x. So once again, we've got the derivative of the first function times the second untouched plus the first function untouched times the derivative of the second function. We can simplify this just a little bit. We can take out e to the x as a factor, and we get e to the x into cot x minus, we get e to the x cot x minus cosec squared x, and that's about as much as you can simplify that there. Right, the second question is now 12.2. y is equal to the log base 6 of cos of 2x. Now, what a lot of you did here was to treat the log 6 as a whole function and multiply it by this over here. And of course, that's a bit of nonsense, because log 6 you can't must have an argument. It must be log 6 of something, and there's no x in here, so it's not log base 6 of x times cos of 2x. It's the log base 6 of this function over here. So it's a chain rule right from the start. We differentiate the outer function, we multiply by the derivative of the inner function, and of course that itself is another chain, and finally we're going to multiply by the derivative of the innermost function. Let's do it. So we've got y prime is equal to, now we want to differentiate log base 6 of something, and we know that the derivative of that, log base 6 of something, is just the 1 over the something, and in this case the something is cos of 2x, but because we're log base 6, we now also need to multiply by the natural logarithm of 6 in the denominator. So this is the derivative of the log base 6 of something. Because we're using the chain rule, we now need to multiply by the derivative of that something. That something is cos of 2x. So the derivative of cos is minus sine. Again, we're using the chain rule because it's the outer function is cos, the inner function is 2x. So when we differentiate the outer function, we get minus sine of the inner function untouched, and only then when we finish differentiating cos of something can we multiply by the derivative of the something, and of course the derivative of 2x is just 2. Quite a lot going on here. Now we can simplify this. Let's bring the 2 to the front, so we get 2 minus 2 sine of 2x in the numerator, and that's all divided by cos of 2x times the natural logarithm of 6. Of course, whenever you've got a sine of something over the cos of the same something, we simplify that to tan. So we've got sine of 2x over cos of 2x. So we end up with minus 2 tan of 2x all over natural logarithm of 6. So very easy marks if you know what you're doing. Just be careful. Use the chain rule, not the product rule. Log base 6 is always the log base 6 of something, and in this case the of something is what's in that bracket. Okay, last one. For your final 2 marks, we've got y is equal to the arc cos of the natural logarithm of x squared. And again, arc cos, some of you treat it as a arc cos times this thing here, but you've got to have the arc cos of something. And there's no x in there, so it's not the arc cos of x times the log of x squared. It's the arc cos of the log of x squared. So nested functions, we're going to use the chain rule. So y prime is equal to, now this gets a little bit tricky, because when we differentiate arc cos of something, Remember, the derivative of arc cos of something is minus 1 over the square root of 1 minus the something squared. And in this case, the something is log x squared, and we have to square all of that. So this is the derivative of the arc cos, where this whole function here gets squared at the bottom over there. Alright, so we've just differentiated the arc cos, the outermost function. We now differentiate the inner function. Now the inner function is the natural logarithm of x squared, which again is a nested function. So we first differentiate the log, and the derivative of the natural logarithm is simply 1 over whatever is in the argument. In this case it's x squared. We leave that untouched, and now we've differentiated the natural log to get 1 over something, and now we multiply by the derivative of the innermost function, which is simply 2x. We can do a little bit of simplification. This x here is in the numerator. We've got an x squared in the denominator, so we can cancel that x with one of these, and we are left with minus 2 in the numerator all over. One of these x remains. I'm going to bring it to the front of the denominator. X times the square root of 1 minus the natural logarithm of x squared with the natural logarithm all squared. You can, if you want, write this in the same way that we write a log, a sine and a cos squared. We can put the squared right next to the logarithm. So we've got x times 1 minus log squared of x squared, and that shows us that we're squaring this whole function. That is quite common notation. I'm not sure how many of you seen it in class, but of course you would have got your full marks if you had left it like that. This is just alternate notation.